Hello and welcome to my modeling project for Calculus 2. Now, in this project we were tasked with picking 4 to 5 everyday objects or objects that we made up and graphing them using GeoGebra so that we can see what they look like when they're circled around an axis. Chosen axis could be y-axis, x-axis, or any given line. So the first object I chose was a simple glazed donut. From Krispy Kreme, of course. And the way that I did this glazed donut was I started out with two quadratic functions being 0.75x minus 2 squared plus 3 and negative 0.75x minus 2 squared plus 6 to create these two quadratic functions that you see here. And then I took an ellipse and graphed it around the two quadratic functions, as I originally tried to just use the quadratic functions, but as you can see here with the lines, the space in between the two quadratic functions, it doesn't really create a great donut shape. It more looks like a squished donut maybe that somebody put in a compactor. But I used an ellipse, and as you can see here, I circled it around the y-axis, and it creates a pretty tasty looking donut in the same color as a glazed donut. Now, the second object I chose was a funnel, which was rather simple, just a basic funnel. And the way I did this was I started off with two functions, y equals x and y equals x plus 1, just two straight lines, diagonal lines, and I graphed those up here, right here, and those create the two lines that you see here. This graph is flipped, but as you can see right here, these two lines are created by those functions, and then I use the functions x equals 1, x equals 2, y equals 0, y equals 2, and y equals 9 to create these horizontal lines, and I limited them to the scope of um, the functions, and then I rotated it around the y-axis to create this funnel shape. Looks like an everyday funnel, just something you'd normally use. And as you can see here, the graph unflipped, and it just looks like a funnel. Not much to it. Now, um, yeah. So I have the next one, which I thought was pretty creative. It's the old hair dryer ping pong ball levitation trick. So if you didn't know, you can take a ping pong ball and put it underneath a hair dryer, and the ping pong ball will sort of levitate above the hair dryer. This video will demonstrate it. So it's pretty simple that a hairdryer levitates a ping pong ball just because of how light the ping pong ball is and the force of the air blowing it upwards. So for this one, I decided to start with the function right here, square root of 1 minus x squared plus 8. Plus 8 just for the height above the x-axis. And I map that around a line, and that creates this ball. It's very laggy here, so I can't really zoom in and show, but I can rotate, and it creates a little white ball. Looks like a ping pong ball. Now, I did some different experimentation with exponential decay functions and linear functions, as I knew that was the type of functions that I wanted to use for this. And as you can see right here, this line right here is the function negative 0.75x e to the x minus 2 plus 4 on this given x interval. And that creates this sort of curve that we can see like in this hairdryer here and in my original sketch of what a hairdryer looks like. Now, after that, I use some simple linear functions to give this bounds, rotated it around the y-axis, and that creates the top of the hairdryer, as you can see right here. As for the bottom of the hairdryer, I chose a function in the form of square root of a minus x squared. Very similar to this original function, except it's much wider, and I ended up going with the function 3 minus 0.07 x minus 3 squared minus 5, just to get it below the x-axis. And rotating that around the given line, y equals 5, sorry, and that creates this circular ovular-ish looking handle attached to this hairdryer, and I use lines obviously to fill in the space here and fill in the space here. Whoops. And that creates this image of a hairdryer holding up a ping pong ball. And for the next object, I decided to go a little more abstract, as this isn't something to my knowledge that does actually exist. But it takes a while to load, but as you can see, it's not very obvious right away what it is. I wouldn't think it would be, but if we look at this, we can see that it's a double hand drill in theory. So there's two drills right up here, and then you have little stems to support the drills. You have a little guard from the drills for your hand, and then you have a little handle down here as well. So what these will do, what'll happen with this is you hold it here. You will hold the drill from the handle down here. The handguard protects your hand from the drill, and you can press the drill up against a rock or something similar, and the force, the compression force from both sides of the drills, along with the spinning of the drills, will drill into sides of a rock, and it makes it efficient for, well, in theory, efficient for mining whatever you're trying to mine. So the way I did this, I used basic line segments. So for here, let me find the rotation. For here, I used basic y equals x functions. This is a slope of -2, I believe, and this is a slope of 2. So that's for the original line of the drill. And then there's a line here for the bottom of the drill, which is just a horizontal line. And I mapped these drill sections around the line, this line right here, which is just a y equals x function with a slope of 1, move to the left 4 units and up 3 units, or left 3 units, up 3 units, sorry. And this side is the same thing, just mirrored on the other side to get the idea that there's two drills. And then what I did for here, the base of it, I wanted to get a sort of perfect semicircle. And my idea at first was to use a square root function, just like I had done with the hairdryer ping pong ball up here, to get that sort of half circular. But I tried doing that, and it was hard to find functions that lined up perfectly to create this like symmetrical or similar shape where there's one on the outside and then one slightly smaller. So I ended up just using the arc function in GeoGebra to create this, and then I used just horizontal lines and vertical lines to create the handle, and I mapped all of this bottom section, this top section right here for the handguard. I mapped it around the y-axis. As you can see, when I turn this up, it rotates around the y-axis in two directions. So if you rotate it all the way, you get the full look. And then for the bottom area here, I mapped it around the x-axis. This just creates a simple cylinder that you can use as a handle, as you can see right here. Now, the final object is the most complicated object, and it is a Gatorade bottle, a simple Gatorade bottle. Now, I thought this one would be easier, but obviously it was not. You can see the immense amount of work I had to put into this, so there was a lot that went into it, but I eventually figured it out. So I started off with this function right here. Let me close this up. This function right here. Let me rotate this around, as you can see. So I started with this function right here. I figured it was best to start with the main curve of the function. And the function I started out on was, it is right here, negative 0.5x minus 1.5x. Let me zoom this in a little bit. So I started off with, it's down here, negative 0.5x, 1.5x. And I originally started off with it being plus 15, and that would leave it somewhere around here. But then when I completed the function, the Gatorade bottle looked very stumpy. It was very short, because it was more like down here this line ended, and then it ended like right around here. But in the end, I just added 5 to all of my units, so I'll be going by that measurement from now on. For this curve down here, I used the function 1.5x minus 6.2 plus 2.23. 2.23 is just for the height to get it above. And I can zoom in here. There's a little curve right here. You can't really see it, but there's a little curve right here, which I use this top function, the square root of x minus 6, all to the fourth power. I used horizontal lines for the top and bottom, as well as the cap. And what I did, the reason why a lot of these say it's from 0 x 6.6 or 6.464 is because I found out that the point right here, the original point was I believe 12 4.64 or 6.464 sorry, existed on this curve, and so I mapped every function to be equal in height and equal in x value to 6.464, which is why it's not on an even point right here if you see the right side of the bottle. And then for the other curves, I used various square root functions. As you can see here, 0.5, both the negative and positive, x minus 5.5, the square root of that, plus 16.51, just to get this curve here. That's for this curve. And then this curve, negative 0.75, this right here, got to here. So all I did was take this quadratic that I found out and mapped every other function, being square roots and negative square roots, to line it up with the rest of the bottle. And the rest of it's obviously just line segments. And when it's fully rotated around, it actually does something weird with this curve down here. It doesn't correctly map it if it's 360 degrees for some reason, which I got a little bit confused about, but if I just go partially wrap it around, you can see the effect it does have, does work. Got the little curve down here. As we see in a traditional Gatorade bottle, you have the little curve at the bottom, straight line, bottom curve, up right here where the label would be, and then a small curve followed by a bigger curve, curve up, and then the cap. And that will do it for my project. Thank you.